Hello folks, it's time for a new video. I was about to finish my processing of this wonderful spiral galaxy here. This is NGC 2835. Unfortunately, it's only visible from the southern hemisphere, but I use a dataset from Telescope Live here. When you have a subscription to Telescope Live, then you can access their pro datasets. And this object here is contained in this dataset. And this is a really deep integration. It's about 15 hours integration, LRGB. But today I don't want to show you the LRGB processing. This is pretty straightforward. The data is really good and ready to use. So no heavy corrections needed. But I want to show you something different today. I want to find the farthest object in this image. When talking about far objects, we are always talking about quasars. And there are not so many data catalogs available for quasars, but there's one central catalog. Of course, I'm using Pixinsight, and I will also do an annotation of this image within Pixinsight. So the idea is that we can see all the objects then here in this image. So first of all, we need a browser, and we search for the proper catalog, and this is called MilliQuast, the Million Quasars Catalog. And this was just a simple Google search, so we can browse this table. And for this demonstration here, I use only a very small portion of this catalog. Only the region of interest for that photo that I'm having here in Pixinsight. So you can grab the full catalog if you want, but normally, this may not need it. So, and this catalog search here is one way to go, but here we can also search for a specific object. And of course we are choosing this bright central galaxy here, NGC 2835, and we define a search radius, which I set to 20 arc minutes, I think, because the sides of this image are something around 23 arc minutes. So radius of 20 should be good. And first we will have a look at HTML formatted table, if there's anything inside. And yes, it is. There are, in this search here, we have six objects. And what this table provides you is, of course, the name, the coordinates, the blue and the red magnitude, and for me, for this purpose here, the most important thing is the redshift. Unfortunately, this object, it will be in our frame, but it don't have a distance given. Yeah, well, but anyway, I think 3 other objects should be visible. So now for a computer use of this data, we need a different format. We can't or shouldn't use the HTML format. So I select on the top here, I choose Excel compatible. That makes the next steps in the processing more easy, because we have to reformat this data slightly, at least slightly. So this is the XLS file, and here we have our data. That looks good so far. And one very important thing for Pixinsight is that we have the coordinates given in decimal degrees, and this is exactly the values that you see here. These are decimal degrees. And for Pixinsight, I just make sure, I'm not sure if it case sensitive, and we have to decide for one specific magnitude, and I will choose, I think, this one as our magnitude. So now, unfortunately, we are not finished here, because Pixinsight can't handle additional columns like the redshift that is given here. So this is just not possible to use it that way. So we I decided to reformat our name column. So we create a new column called name, and we remove this one. Don't care. And I will concatenate some text. This calc software, this spreadsheet software is set to German. Therefore, you see German commands here in your language that may differ. So I want the name, and I want the redshift. Redshift is always called set. And I want to add this redshift. Yeah, this is straightforward. Okay, so this is the data I'm interested in. And now I will create a proper text file. And therefore I move to my image folder and create a new text document, quasarcatalog.txt, that's fine. And now grab a text editor. And here you can see another important thing. We need tab separated columns. And of course, we need decimal values with a point and not a comma. So we replace all commas with a point. So that's it. So now we have our very, very simple and small catalog prepared with a name, including the redshift, the right ascension, the declination, and the magnitude. And this is what we use now in Pixinsight. First of all, to do an image annotation, we have to solve the image that we have very precise determined coordinates for this image. So that was solved before from the raw stack. So this data looks very proper. Let's just try it. Okay, here we are. What this script does is it shows you also the error values, but all these matches are looking very precise. And now this image is solved and we can check out our render annotate image script. So first of all, I always use some of these catalogs, for example PGC with very faint galaxies, and Tycho 2 for the brightest stars in this field, NGC of course. And then I also use, just a moment, I don't use the Gaia catalog because there are too many stars in it, but I add a custom catalog. And for this custom catalog we can choose, or we choose our prepared text file, and now we can decide what to display, but you know, there is not much in it. We already set name, and I also, let's just print out the magnitude. I want another color, different color, and let's do bold. That's okay. Also show markers, and then we don't need to apply an STF because the image is properly stretched, and I just annotate the image. You also can do, for example, an SVG overlay or transparent overlay if you want to process it more in than, let's say, Photoshop or some other image processing software. So let's stick with annotate. And then this looks good. Okay, here we have our annotated image. That's a matter of seconds. And what we can see is, the main galaxy here is properly annotated, and we have also our coordinate grid in it. And we see some of the fainter PGC galaxies here. They are not that much as I expected, but the other ones here in this image are just too faint. They're too faint, they don't have a PGC designation. And you see Tycho stars here. But the most important thing, why we did all this stuff here, are the blue ones. And these are our annotations And here you can also see the fit is really good. It's point on. This is this object here, 19.4 magnitude, or for example this one here. This is also an object very, very far away. To be honest, that's nearly insanely far away. So what does this mean, Redshift 2.3? What is this? You know, the universe is expanding, and because of this, all objects are receding from each other, all objects moving away. And when doing this at a high speed, their light is shifted in the wavelengths from higher to lower wavelengths. And lower wavelengths means a redder light or more red light. And now the thing is, the more away these objects are, the higher the redshift is. And this means, and you can calculate this by taking the shifted spectra and build or calculate the ratio to a non-shifted spectra. And this ratio is here, for example, 2.3. You can now calculate something out of this value. Therefore, we need a redshift to distance calculator. For example, this one here. This was just, I found this by Google, this is from NetWrite from the UCLA. And yeah, here we have now to assume some constants. For example, the Hubble constant. If you're interested in what this all is and how it is calculated or measured, just head over to Wikipedia and have a look there. Hubble constant. This is really important for cosmology. That is one of the fundamental values in cosmology. For the moment, we just assume it to 69.6. And now here we enter our redshift of 2.3. We assume a flat universe, and then some values are calculated. First of all, the age of the universe is calculated. 13.7 billion years. This is the current common value, common agreed value. But now the interesting thing starts here. And this is the age at this redshift was 2.8 billion years. That means the light was transmitted from that object, quasar obviously, when the universe was 2.8 billion years old. And that means also that the light was traveling 10.8 billion years until it reaches the Earth, this telescope, the camera, and finally we see it here, 10.8 billion years. That's crazy, isn't it? For example, the other one here, we have a redshift of 1.2. Let's give this a try. The light travel time here was 8.5 billion years. Also insanely far away. That's for sure. Let's get back to this. That you get a better idea what I'm talking about. I found this really nice scheme of the expansion of the universe, also Wikipedia. And what this shows us is, first we have here the Big Bang. Point of the Big Bang, a very, very fast expansion. And then over the time it still expands until now, or even now. Of course it's continuing. And so that means we are here, and the light with 2.8 billion years was transmitted somewhere around here at this point of time. So this is really near the edge of the universe. And I found this really interesting to look that far in time and space. So now there was still no real distance. I never mentioned a real distance. And that is right, because it is not that easy to tell you a real distance. For astronomers and cosmologists, the redshift is the value that they are working with. That is the common agreed value, because when you want to calculate a distance and all these values here, you have to assume your Hubble constant and so on. And these values are still under investigation. But if you assume these values as true, then you have to take into account that because of the expansion of the universe over these 10.8 billion years, the distance increased between the Earth and this object. It's always increased over time. And when we take this expansion into account, the real distance to the object is 18.55 billion years from now. So this is crazy, isn't it? This is a value that I even can't imagine that. So this was just my very simple approach to bring you to the outer regions of the universe and to the edge of the universe. I hope you like it, and now I'm also showing you the final LRGB pretty picture here, so stay tuned. If you like it, please feel free to give me a thumbs up and subscribe to the channel so I can provide you some more content like that, or also other things related to astrophotography. Thank you, see you again, bye bye.